here we have a car that's traveling 30 meters per second west, and then it takes 5 seconds to turn to a new velocity of 50 meters per second west, 50 degrees south. So we're going to define in this case that south and west are going to be positive, just because those are the coordinates we're dealing with. So it makes life a little bit easier this way. So if we draw our triangle, we're going to note that we have an original velocity going this way, and that's 30 meters per second. And then we're going to go west 50 degrees south. So that means we're pointing west and then turning at an angle of 50 degrees. So we're going to maybe go down around like this, and our new velocity is 50 meters per second, taking note that this angle here is our 50 degrees. We can add our vectors head to tail, and our triangle is going to look something like that. So if we recall, acceleration is equal to your change in velocity, or v2 minus v1 over t. What we're going to do now, because we have this obtuse triangle that might be difficult to work with, is I'm going to take the fact that I know that I have v2 minus v1 up here, and I'm going to use that to my advantage. So we can agree that v2 minus v1 is the same as writing v2 plus negative v1. And I'm going to take that idea and redraw my triangle a little bit. So v2 is going to stay the same. That is 50 meters per second with a direction of west 50 degrees south. And v1 is now going to be equal to negative 30 meters per second east. So we've made this little change here just to allow us to not have to deal with this obtuse triangle that you can see on the left of your screen. We're going to be able to redraw our triangle a little bit as an acute triangle. So we still have our v2 just coming in at 50 meters per second at an angle of west 50 degrees south. And we have our new v1, which is going to be somewhere down here at 30 meters per second. Don't make the mistake of thinking that this is necessarily a right angle triangle. It might be, but it might not be. And we've added v2 plus negative v1 in this case. Okay, so now what we're going to take a look at is how to solve for the missing side here. So this is v2 minus v1 or v2 plus negative v1. We're going to need to know this angle theta in here, and we're not assuming that the angle down here is a right angle triangle. This we do know to be 50 degrees though, because of a Z pattern that emerges with the 50-degree angle up here. So we can solve this by using our cosine law. We have enough information. We have the angle opposite to the side we're solving for, and then we have two other sides. So I'm going to write, so v2 minus v1, we can also write as our change in v. That'd be another way to put this. So our change in v, or v2 minus v1, is going to be equal to the square root, and we're going to put our cosine law in here, of 50 squared plus 30 squared minus 2 times 50 times 30 times cos 50 degrees. You can put all of that into a calculator and you're going to end up with the square root of 1471.7, which means that your v2 minus v1, or your change in velocity, is simply 38.4 meters per second. So now we have our change in velocity. We have our value for v2 minus v1. We can go ahead and use sine law to solve for the missing angle at the top there. So that's going to be sine of theta divided by the side opposite to theta, which is 30, is equal to sine of 50 divided by the sine opposite to 50, which is 38.4. We can then rearrange so that theta is equal to sine negative 1 30 times sine 50 divided by 38.4, which gives us an angle of 36.8 degrees. So again, this angle right here, it's not necessarily off of the vertical, so we can't assume that. It's close, but it's not exactly right. We can come up with this angle two ways. We're either going to look at this whole angle here, which might be the easiest way to do it, or whatever this tiny angle in here is. So we know that the entirety of that angle is going to be 50 degrees plus 36.8 degrees, which gives us 86.8 degrees. So our directionality would be something like west 86.8 degrees south, or conversely, we could say south 3.2 degrees west for coming off the horizontal instead. Now with all that information, we can go ahead and solve for the acceleration, which is this equation that we started with at the top of the example. So acceleration is equal to delta v over t. That leaves us with 38.4 meters per second south 3.2 degrees west over your time, which is 5.0 seconds given in the question. So that leaves us with a final acceleration 7.68 meters per second squared, and always include the direction, since it is a vector, south 3.2 degrees west.